Selective recognition between molecules plays a fundamental role in nearly all biological and chemical processes. In biology, errors in molecular recognition can lead to disease. In chemistry, improved molecular recognition enhances the performance of catalysts, medicines, and materials. Researchers have now developed a new strategy to improve molecular recognition between two DNA strands. Two different DNA strands are added to a complementary template strand. Molecular recognition between the strands leads to the formation of red and green duplexes. The red and green strands are in dynamic exchange, and the ratio of red to green duplexes is determined by their relative thermodynamic stability. The strategy for improving molecular recognition begins with the addition of a blue fuel strand that is fully complementary to the template strand. All red and green strands are completely displaced due to the higher stability of the blue duplex. The green strand is displaced slightly faster than the red strand. The fuel strand contains uracil nucleobases, which are eliminated by an enzyme present in the solution. This reduces the stability of the blue duplex and allows the red and green strands to hybridize with the template again. However, the displacement of the blue waste strand by the green strand occurs very slowly because the green strand attaches poorly to the template. On the other hand, the red strand can attach efficiently, causing rapid formation of the red duplex. Once the red duplex has formed, efficient exchange with the green strand can occur again. These kinetic exchange reactions continue as long as fuel strands are present in the solution. Under these conditions, the ratio between red and green duplexes is no longer determined by their relative thermodynamic stabilities, but by the relative rates at which the red and green duplexes are depleted and reformed in the reaction network. The researchers have shown that under non-equilibrium conditions, the ratio between red and green duplexes increases from 2:1 to 6:1 compared to thermodynamic equilibrium.